This is our introduction to exercise 12.4 on confidence intervals for proportions, page 550 of your textbook. A couple of definitions that we have to get through. First thing is confidence intervals. So we analyze samples to further understand a population from which they are drawn. We know that what is in the sample, and using this we can infer something about the population. So there are a couple of key definitions there. I'm going to start with the bottom one. A confidence interval for P is an interval estimate for the population proportion P. Essentially what happens is I'm saying, let's pick a number, I'll say 95% because that's a conventional percentage. There's a 95% chance or 95% probability that, or 95% confidence that a certain value is between there and there, right? So essentially what we're going to get is a range or an interval of values. Our point estimate is a single valued estimation of the population proportion P from the sample proportion. We'll get to that in a moment. This formula you can see underneath is very, very important. Please make sure you have it in your resource book or something like that. An approximate, and again you'll notice approximate, right? An approximate 95% confidence interval for P is given by this formula here. You'll notice that it's P, or the average, or the estimate, sample proportion, minus 1.96 times this square root. Now this square root is very important, we'll come back to that in a moment. Something I'd like you to add to the side of it is, this is all considering, that's meant to be a star, considering large sample, or large n, we'll just do that. So NP and n bracket 1 minus b, you might see it in the textbook as q, same thing, needs to be greater than 5. So this is all assuming a large sample size. In here, P is the population proportion. P hat is a sample of the value, is a value of the sample proportion, and n is the size of the sample from which P hat was calculated. I'm going to go quickly through why 1.96 is that special number. What I'd like you to do in your calculator is open up the main setting. I'm going to very quickly draw out a diagram for us. Let's use 95% as an example, right? Because 95% is probably the most common one. If this is 95%, to find our Z value or standardized score, this makes sense to be 2.5%. Of course it makes sense. If the middle needs to be 95%, where that middle is our confidence interval, well that left-hand side needs to be 2.5. So what I can do is use my inverse norm. So I'm going to open up my calculator. I'm going to go into my calculator, put an inverse norm, put in my correct parameters. Of course, you can do this from the right-hand side as well, but just for this, we're going to use the left-hand side. So, as soon as the calculator opens, there we go. I'm going to go into my main. I'm going to go interactive distribution, my continuous, so not continuous, inverse, norm CDF. Left center needs to be 0.025 or 2.5%. I'm going to leave my standard deviation and my mu as you can see. So we end up with a value of negative 1.9599, etc. If you can round it, it's approximately 1.96. That is just the value that we end up using in methods. If the question is, for example, 90% confidence interval, we can do the same thing. If it's 90% in the middle, the left and right side need to be 5%, correct? So I can do the same thing, and I can change that to 0.05. And we end up with our value for our 90% confidence interval. That 1.96% from our 95% interval is this value right here. Of course, plus or minus, it's symmetrical, so plus or minus. And depending on what percentage confidence interval, we will change that value, right? I'll provide you with a general formula for it later on, but we're just going to, for this case, focus on the 95% interval. Let's look at this example. Find an approximate 95% confidence interval for the proportion P of primary school children in Australia who regularly use social media. If we select a random sample of 20 children and find the sample proportion to be P hat is 0.7. I'm going to start by writing out my parameters here. P hat equals 0.7 and I know n equals to 20. What I'm going to do next is I'm going to focus on that square root, the square root of P hat, etc. So I'm going to copy that down first. Just from the formula from above, 1 minus p hat over n. And if we substitute it, of course, we end up with square root of 0.7 multiplied by 0.3 over 20. which using CAS is 0.1025, approximately. Okay, let's do a 95% confidence interval. So a 95% confidence interval, again, is because it's a range of values, really we should be writing from here to here, right? So we're going to use our curve brackets, we're going to say equals to, and we're going to go with, and the formula above is our p hat minus 1.96 times that value. So it's going to be p hat, which is 0.7, minus 1.96 multiplied by the value we just found, which is 0.12025, sorry. At this stage, we've actually rounded twice for methods, just like how we use an acceleration of negative 10 for methods sometimes, rather than negative 9.8. We can just use 1.96. It's not an issue with that in methods 3, 4. However, 0.1025 is a rounding already, so please make sure you use the original square root, 0.7 times 0.3 over 20 in your calculations. Of course, the other one is going to be 0.7 plus the exact same thing. There's no issue with you writing the rounded value, just make sure your final answer has was using the exact value. This question doesn't say, but we're going to keep it to 3 decimal places. Putting that in the calculator ends up with 0.499, 0.901. That's the confidence interval, which means, and you'll notice that 0.7 is in the middle, which means that from a probability of 0.499 and to 0.901, sorry, I have a 95% confidence that whatever value it is, it's going to be between there. It's not guaranteed. Of course, it's possible that in a sample of 20 children, none use social media, right? But it's 95% probability that confidence, I should say, that it's going to be between these two values. What we're going to do is we're going to start slowly changing those variables to see what happens to this function or this value, this answer, as we increase or decrease the sample size, etc. Let's turn the page. This is the answer from before, 0.499 to 0.901. Please be very careful to say it, not to avoid this. Now, this is something that in the new study design, Vega has neglected a little, but by definition is incorrect. So, the probability that P is between 0.499 and 0.901 is not 0.95. A statement like this is meaningless as P is a constant and either does or does not exist or lie within a stated variable. The correct interpretation, and this is really essentially just a copy-paste, you should be able to just copy-paste it into your answers. We expect approximately 95% of such intervals to contain the population proportion P. If you look on the diagram on the right-hand side, there are 20 different samples, each line and dot representing one sample. The round dots indicate the value of a sample estimate in each case. You'll notice that that dot is, of course, it's a singular value. It either is or isn't. All the intervals except one, so in other words, 1 out of 20, sorry, 1 out of 20 or 5%, have captured the value of population proportion as would be expected in the case of a 95% confidence interval. Really what I'm trying to get you to take away from this is don't write that original that notation of probability. Write out if the question says interpret this, write approximately 95% of intervals contain the population proportion P. That's really all you need to write. Of course, the percentage may change depending on the question. Let's look at using our calculator for this. A survey found that 237 out of 500 undergraduate university students intend to take a postgraduate course in the future. Find a 95% confidence interval for the proportion of undergraduates intending to take a postgraduate course. We're going to hop into our statistics menu on our calculator. So go to menu, statistics, and just make sure you clear anything that's still there. What we're going to do next is we're going to go to calculator, or calc, and then go to interval. So we're calculating interval. So statistics, clear everything, calc, interval. It's most likely that that your first option is 1 sample Z. Just make sure that says 1 proportion. So 1 PROP, Z interval. Again, you can always select the help button to show you which one you're focusing on or what that means. Select next. Would you like me to go back for a bit?
Yes, please.
So, in your calculator, you should have, let's go again, menu, statistics, make sure everything's clear, calc interval. And then once you've done that, change it to 1 prop zint. There shouldn't be an additional option after that. If it is, you've selected the wrong type. So it's interval 1 prop zint. Again, I always like to put in the help option just so I make sure I know what I'm talking about. It says C level, which is our confidence value. A lot of students accidentally write 95. Just make sure, remember, the help tells us C level needs to be between 0 and 1. So 0.95. Our X value is going to be, well, of course, the number of successes. So 237, that's what the question says, 237. And N is the number of trials or number sample size. In this case, it's 500. Once you've done that, hit next, and voila, it gives you your low and your upper. Coincidentally, also gives you a p-hat, but we'll ignore that for now. So, if I'm putting the values in of, and I'm putting my parameters down here, 0.95 for my confidence interval, 237 for my successes, 237 for my successes, and 500 for my sample size, we end up with a value of 0.430. We round it to 3 decimal places, to 0.52, no, 0.518, we'll go with that. It's a 95% confidence interval using the calculator. Any questions? Okay. Let's go into a little bit more depth. Our precision and margins of error. If we're finding an approximate 95% confidence interval for the population P, etc., 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 if we change, and you'll note this is very similar for example 42, which was this one up here. The only difference being that our sample has gone from 20 to 200. What do you think will happen to our interval, our confidence interval? We're still keeping with 95%. What would happen to our confidence interval if we increase the sample size from 20 to 200? Is it going to be wider or is it going to be narrower? You don't need to answer me, just have to think about it. If we increase the sample size, will that result in a wider or a narrower confidence interval? I'm going to start by writing my parameters. P hat equals to 0.7 and n equals to 200. I'm going to use my square root from the formula. I'm just going to rewrite that above, which gives us an answer of, and I'm skipping forward, 0.324. Do the same process. You put in the calculator and you do your p hat minus your blah blah blah, 1.96 times, etc., and you'll end up with a confidence interval 0.636 to 0.764. Let's compare that with our previous one. So I'd say that has about a difference of about 0.13, something like that. If we look up at our previous one, the difference here was about 0.4. It's notably different. As we increase our sample size, it makes sense that the actual outcome of whatever it is, right, reflects the population proportion more accurately. Of course, it is still possible, right, that you have a value that's outside of this, but it's more likely to happen, so that if we maintain the same confidence interval, we can keep with the same, with a narrower interval. Later on, we'll look at what happens if we change our confidence interval, but we'll get to that in a moment. Let's look at our margins of error. The margins of error is the distance between sample estimate and the endpoints of the confidence interval. So for a 95% confidence interval, this is literally this component of the formula. Right, that's what we're used to. For specifically a 95% confidence interval, remembering that that changes depending on what your confidence interval percentage is, it's 1.96 times this. That's your margin of error. And if you rearrange it, you end up with this, n equals to etc. You don't really need to know this formula, this bottom formula. You could just substitute and solve as per usual, but that's just giving it nice and easy. In general, where our confidence interval, of course, is a decimal value, not a whole number, well, unless it's 100%. P hat minus k, where k represents that confidence interval value. Okay, it's not 0.95, in that case it's 1.96, but depending on what your confidence interval is, you'll use your inverse normal, CDF, to calculate it. Okay. Would you like a quick refresher on that at the very start, or you're okay with us moving on? Can you look at me with fear if you'd like me to recap it? Okay, very quickly. Let's say we've got a There we go. Let's say we only want an 80% confidence interval. If that's 80%, it makes sense that we want this side to be 10%. So we just go into our calculator, we go to our main, we go interactive distribution inverse norm, and we put in 0.1, my apologies, and that would be our value. So instead of 1.96, we would use 1.28 in that calculation for an 80% confidence interval. Let's move on. Example 44. Determine the sample size required to achieve a 2% margin of error. So now we're finding the n value in an approximate 95% confidence interval for the proportion p, etc., etc. The rest is the same. So what I'm going to do is I'm going to write m equals to 0.02. Because we've said the margin of error is 0.02, I'm going to use my formula. It does say 95% confidence interval, so I can keep it as 95%. So I'm going to go equals 1.96, don't need to change that, square root of 0.7 times 0.3 over n. Of course, n being our unknown variable in this case. You can solve this using the calculator, absolutely no issues, or you can use this formula. This is just a rearranged version of it. So I'm going to write or n equals, have I gone too quickly? N equals 2, and I'm going to use the formula from above, 1.96 over 0.02 squared times 0.7 times 0.3. So you can either write out the first one and solve for n, or you can just use a second equation. There isn't an issue, but in most cases, not in most, in all cases, you'll be using a calculator for this. So for exercise 12.4, just use your CAS for all the questions. If you put this in your calculator, end up with a value of approximately 2016.84. Now, of course, it says determine the sample size. It doesn't mean 0.84, right? So if we're saying that means 2017. If we reduce it, even if it says 2016.1, if we reduce that value, we're going to end up with a margin error that's different. So we want to round up in this case. So therefore, n equals to 2017. Last page. Like ever, last page. Calculate and compare the 90, 95, and 99 confidence intervals. I'm not going to go through every single step, but we know the 95% one. The question itself is the same as prior, or the rather context. So that's going to be from 0.63 to 0.764. I've just copied that from above. Let's go with the 90% one. The 90% interval, we're going to use the value from before. So of course I can go in my calculator, put in my inverse norm, etc. Change this 0.1. We're going to make that as 0.05 because it makes sense that it's 5% on each side if we're doing that. So that gives us negative 1.645, round it to 2 decimal places. So, and I'll go through the whole process of this one. That's going to end up being 0.7 minus 1.645. 4, multiplied by the square root of 0.7 times 0.3. This is the same thing as we've done prior. 0.7 plus 1.645 multiplied by the square root of 0.7 times 0.3, again over 200. Whew. Put in the calculator. 0.647, 0.753. Now, it's notable to say that as we actually, let's look at our values. Our interval, confidence interval of 90% has a difference of, I'd say, about 0.1. Maybe a slight difference, but about 0.1. If you look at a 95% confidence interval, that changes as well. Well, now it's gone from 0.1 to about maybe 0. Where's that? You know what? Let's just do the 99% confidence interval. We'll compare that. 99% confidence interval, and I won't go through all the steps, but it's the same thing. You end up with 0.616 to 0.784. What do you notice? As we increase our confidence interval, what's happening to our values? At 90% interval, we have a difference from lower to up about 0.1. If we got to look at 95%, we have about maybe 0.3, something like that. As you move up, you have a 0.1, so not 0.6, 0.13 from 95%, and for 99% you have a difference of about 0.17, something like that. As you increase your confidence interval, right, in order for you to be more confident, it makes sense that your interval that you're focusing on needs to be wider as well. Being more confident in that the confidence interval captures the true value of population proportion means that a wider interval is required. It makes sense. If I wanted to be 99.9% sure that I know the height of students in this classroom, I would just give a very, very large range. It makes sense. So as we increase the confidence interval, our range or interval will get wider. As we increase our sample size, our confidence interval will get narrower. That's it.